Standard deviation sounds silly. How can deviation be standard? But the name is exactly correct. A more descriptive name is a consistent way to measure distance between the sample average and any sample observation, regardless of the measurement units. That's more descriptive, but not very catchy. Instead of trying to imagine standard deviation as a definition, think of it as units on a scale, like centimeters. On a centimeter scale, the marks are 1 centimeter apart. On a standard deviation scale, the marks are 1 standard deviation apart. Suppose we collect a sample of 10 salamanders and measure the length of each in centimeters. The average length is 5.4 centimeters, with standard deviation 0.6 centimeters. To measure the difference between the length of an individual salamander and the average length, we need a scale marked in centimeters. If the observations are converted to inches, we need a scale marked in inches. But the salamanders haven't changed. The only change is what scale we use to measure them. We need a scale that can handle centimeters and inches, and any other measurement units, such as weight, speed, temperature, luminosity, anything we can imagine. That scale is number of standard deviations. The standard deviation for the salamander sample is 0.6 centimeters. On the standard deviation scale, the distance between scale marks is 0.6 centimeters. The number of standard deviations from the average is the difference between the observation and the average divided by the standard deviation. A 6 centimeter salamander is 0.6 centimeters from the average. The difference is divided by the standard deviation. The centimeters in the numerator and the denominator cancel, leaving only the number of standard deviations. The 6 centimeter salamander is 1 standard deviation above the average. We can improve the scale by labeling the number of standard deviations above and below the average, putting 0 in the middle. A salamander with length below the average will be in negative standard deviations. A salamander with length above the average will be in positive standard deviations. Now, suppose we get a sample of cow weights in kilograms from a nearby dairy farm. The average weight is 550 kilograms, with a standard deviation of 30 kilograms. To measure the difference between the weight of an individual cow and the average weight, we need a scale marked in kilograms. Or we can use the standard deviation scale as used for salamander length, except that now the distance between marks on the scale is 30 kilograms. A 580 kilogram cow is 1 standard deviation above the average. A 520 kilogram cow is 1 standard deviation below the average. Now suppose we have a sample of car fuel tank capacity measured in liters. The average is 55 liters with standard deviation 9 liters. We can again use the standard deviation scale, but now the marks are 9 liters apart. Distance from the average in number of standard deviations can be used for any sample and any measurement units. We can also put in fractions of standard deviations, depending on how precisely we want to measure. The actual value of the standard deviation is different in all of these, but the marks on the ruler are always 1 standard deviation apart. The number of standard deviations from the average is called a z-score. The calculation of a z-score for an observation, average, and standard deviation is the observation minus the average divided by the standard deviation. Calculating the z-score is called standardizing. The name is not an accident. Difference from the mean is measured in standard deviations, and standardizing comes from that. We rarely will need to have more than 3 standard deviations above and below the average. The reason is explained in Betting on the Standard Deviation.